All right, hey y'all. We're gonna do chapter 2 here. So we're gonna talk about two different kinds of acids and bases. One being Bronsted-Lowry, which is gonna be the vast majority of what we talk about, and then the other being Lewis acids and bases, which are a little bit different, and we'll talk about that when we get there. So let's start with Bronsted-Lowry. That's kind of the more common one you're used to. In Gen Chem 1, we saw that an acid was a proton donor. When we talk about proton, we're talking about an H plus donor, and Bronsted-Lowry base accepts that H plus. All right, so Bronsted-Lowry acids, this list right here is pretty common. Anything that usually starts with an H is a Bronsted-Lowry acid. The bases have to have either a lone pair of electrons to accept an H, or a negative charge is really helpful as well. It makes it a little bit easier to see where that lone pair is coming from. All right, oh, in addition, we can also have, they didn't draw it here, but I probably should put it, anything that's a double bond or a triple bond can also accept an H. All right, so which compounds here are going to be acids in this first one? Remember, in order for it to be an acid, let me actually do a much better job doing this. So an acid, it needs an H. And the Bronsted-Lowry base, it needs either a lone pair, a double bond, or a triple bond. And those will allow it to accept a proton. All right, so in going through this, it says which compounds are acids. Remember, an acid just needs an H. So this one right here, I'm gonna switch colors, pen real quick. That one has an H, so it's good. NH3's got an H, so it's an acid. Does CCl4 have an H? It does not, therefore it won't be a Bronsted-Lowry acid. Moving on to the bases, again, it needs a lone pair, double bond, or triple bond to be a base. Here we have CH3 bound to a CH3. To remind you, that would be, because I know we're still kind of fresh and learning our structures and stuff. So that's what that would look like. As you can see, that we'd call it ethane. As you can see, there's no double bond, there's nothing to accept it, and this would not work. Then we have this, where we have a CH3 put into parentheses with a C to an O minus. What that would look like is this. We'd have a C, which is bound to an O negative. Remember, we know that O negatives are going to be doubly bound, or singly bound. And then we have 3 CH3s coming off of that. You already had your answer though. As soon as you saw the negative charge, you knew that there had to have been an extra lone pair, and this could act as a base. All right, and last but not least, we have this one where we have a C triple bond is a triple bonded to another CH. This is ethine. And again, here you can see it's got a triple bond. We said it needs a lone pair, a double bond, or a triple bond to be a base. So this triple bond makes it a base, and that works. All right, now let's do this one where it says classify each one as an acid, base, or both. So here I have an oxygen. Anytime you have oxygen, unless it's got a really funky charge, which would be a 2 positive charge, which you really don't see, it's got a lone pair on it. So this one would absolutely act as a base. It also has an H, so it's an acid. So that's both. This one, we can see it has an H, so we know it's an acid. Is it a base though? And remember, it needs a single bond, or it needs a double bond, a lone pair, or a triple bond. It doesn't have those, so it's none of those, it's just an acid. So this guy's just an acid. Last but not least, we get to this one. Does that have oxygen on it? Sure does. Remember, when we talk about oxygen, we know that it has to have a lone pair on it. So that makes this a base. And the other question is there hydrogen in it? There is, and that makes it an acid. So it is both. So both, acid, and both. In case you wonder how to draw this thing, we haven't really gotten into ethers yet, but it would look something like this. And then on this carbon going to here, there are 2 oxygens. One would be up here, and one would be right here, and coming off that oxygen would be a CH3. Just in case you want to draw the Lewis structure, because that's a funky one we haven't seen. All right, moving on. So in this case, it says determine which compound is the acid and which is the base, and draw the products. Okay, so remember, something that has a stronger negative charge is going, and this is from Gen Chem, something that has a stronger negative charge is going to be something that really wants to accept a proton. Remember, a proton's a positively charged thing. We always draw arrows from the negative to the positive. We always use arrows. The base starts at the electrons and it goes to whatever it's going to grab or wherever it's going to move. So it wants us to draw the products. I'm going to go ahead and also do the arrow pushing here. All right, so in this one, I see an H right there. There's also, oh, there's no other H's, just an H right there. And then over here, we have this negatively charged thing, and it's not going to be willing to give off a positive and become more negative. So again, negative stuff loves H plus. I don't know why I wrote number. H plus is what I was going for. Okay, so this negative is going to go over here and grab that H. So this one is the acid because it's giving off an H, and this one is the base. All right, so it took on that H, and then over here we'll draw the products. We've got a Cl, and then we go a double bond with this oxygen here, and now when we took that H, remember you took an H plus, you're going to be left with a negative charge here. So essentially what happened is, if I were to zoom in on this, just this part right here, that took the H plus, but these electrons then went to this oxygen right there. Okay, I know I need to switch pens. It's probably hard to see pen. Okay. Anyway, so this would be our product, and then we'd also have this OCH3 has now taken on an extra H, so it's HOCH3 like that. All right, let's move on to this one. Again, we're looking for the acid and the base. I see a negative charge here. I immediately think that's going to be the one that's taking the H plus. And so you look here and find an H plus that can be taken. None of them actually can, except for that one. So it's going to whoop, grab that sucker. And then remember, those electrons are then going to go on to that triple bond right there, this carbon that's sitting right there between the triple bond and the single bond. All right, so we get Cl, Cl, Cl. And now we have this extra lone pair that came again from this hydrogen bond right there. That sucker's now negative. And you have an H, bonded to an H, in other words, H2. Okay, so again, this one, the one that gives off the H is the acid. The one that takes it on is the base. And you could do, and then you could look for the conjugate. So if this was the acid, this is going to be its conjugate base. Both of those were the conjugate base, and these are the conjugate acids, just to remind you of conjugates. All right, so it says draw the products formed when mixed with HCl. HCl is a strong acid, so it's going to be the thing that's giving off an H plus. Your question is, who's taking the H plus on? All right, well, remember, the base has to have a lone pair. It's got to have a double bond or a triple bond in order to accept an H. So, although it's not drawn for you, remember that the oxygen right here is going to have 2 lone pairs on it. The oxygen right here also has 2 lone pairs. Yeah, 2 is right. And then this one has 1 lone pair, and this nitrogen has 1 lone pair. So when we're talking about where the electrons come from, they can only come from the lone pair or double or triple bond. I don't see any double or triple bonds here, so I know they're coming from lone pairs. Okay, so what's going to happen is HCl is going to give off that H plus, and it does that when this lone pair right here, or I could have done it from over here, grabs that H and takes it on. Then it's a strong acid, so I'm just going to use a one-way arrow. Then we get this over here. We still have the O. This still had an H on it, but now it has a new H on it because it took it on. And when it took it on, now all of a sudden it didn't lose this lone pair that was over here, right there. So it has now a positive charge. that Cl minus, remember it was, or that Cl, it was HCl. When that thing came over and took that H, those electrons went onto the Cl, which already had, by the way, 3 lone pairs on it. So we're left with a Cl minus. All right, we do the same thing with this one. I know this is coming over here, grabbing that, and then I'm going to be left with the Cl with an extra lone pair on it. So we've got 2, 2, oh, and then a 2, 2, and then it's got a new H on it. We still have a lone pair on there, and it's positively charged, plus a Cl minus. Okay. On this one right here, same thing. The only place that this can come from is a lone pair right here. It's going to grab that H, those electrons are going to go onto that Cl, and we'll have N to an H, to a methyl group up top, to another methyl group right there, and it's going to be now positive charged. You can calculate the formal charge of this. Again, valence minus sticks minus dots, 5 minus 4 sticks minus 0 dots, plus a Cl minus. And last but not least, this one. So we have 2 dots on this nitrogen. They're going to come over here, whoop, grab that sucker. Again, that bond is going on the chlorine. And we'll be left with this beautiful pentagon. Whereas before it had 1 H and a lone pair, now it has 2 H's and no lone pairs. And we still have that chlorine minus. One thing to always check, that should have a plus sign, is that all the charges on both sides add up to equal the same thing. So over here, this was neutral and this was neutral, no charges were written. And over here now we have a positive and a negative, positive cancels negative, and that works, so all the way down. All right, acid strength. You're just gonna wanna go ahead and memorize these pKa's. So that way you can just pull them up when you need them. But just a reminder that Ka equals products over reactants of an acid-base reaction. So for example, if you have HF and you put that in water, it'd break down into H plus and F minus. Why am I writing iron? I don't know. F minus. Okay, these are our products. These are our reactants. This is actually double bonded. All right, so if we have a whole bunch of products, if we're making a whole bunch of this, in other words, if we're actually using an acid the way it's supposed to be, this sucker is giving off its H plus. Products over reactants, this number would be high, that number would be small, and our Ka would be big. So really big Ka means stronger acid. But also keep in mind that the pKa is the negative log of the Ka. So you get the opposite. Small pKa means stronger acid. So really low pKa means a stronger acid. So for example, HCl, which is pretty strong, has a pKa of -7. It's a very small pKa. As opposed to this methane down here, a CH single bond, that's going to have a pKa much higher of 50. So this would be a very, very weak acid. It would actually be a much stronger base. Well, if it had a lone pair on it. All right, let's go estimate based on those that you just memorized, because you already memorized them super fast, what these are. You'll see that NH3, that's got a pKa of about 38, so not super strong, right? It's a pretty weak acid. We didn't have exactly this, but we saw something, an OH. So we had a carbon bonded to an O to an H. I'll show you this. Right here, we had carbons, and then an O, then an H. Very different than this one right here. In fact, I'm going to break this one down for you real quick before I get too ahead of myself. This number 2 right here is a carboxylic acid. It's pretty important. C double bonded to an O, H, and then sometimes whatever's over here changes. In this case, they have it as a methyl group, CH3. This right here is a relatively strong acid. See its pK of 4.8. And it's not an actual strong acid. I need to be careful how I say that. But it is a stronger acid relative to many others. And we'll talk about those reasonings here in a little bit. But just wanted to let you know what this thing actually looks like. This one is not that though. This again is an OH, it's an alcohol, as we'll come to know it. And it's bonded to some alkanes. So this guy is very much like the ethanol we saw over here, right there. CH3, CH2OH, so it's got a 16. Ah, do you recognize this? Double bonded to an O, to an O, to an H. That hopefully you recognize as carboxylic acid. That sucker's 4.8. All right, now we have a variety of different ones. So this first one, I see single bonded carbon, single bonded carbon, single bonded carbon, single bonded carbon to a hydrogen. Nothing special about this one at all. That's the 50. That's like a methane. That's an alkane group. Here we have double bond though. So if we went back to this table, when we have a double bond and an H, it's about 44. So it's a pKa of 44. And all these, of course, are about. They're affected by things around them. And then here we have another NH3. Do you remember NH3? Or N bonded to 3 things is going to be about 38. So if I asked you of all these hydrogens, which one is the strongest? Which one's the strongest acid? It's going to be this one right here. And that this hydrogen right here wants to come off and be donated more than any of these other hydrogens. All right, so now I ask you to draw the products of each action. I'm gonna get some paper here. So a little more space to write bigger. Draw the products of each reaction to determine the direction of the equilibrium. All right, so this first one, I'm gonna redraw it. We have a C, double bond it to a C. Plus this hydride ion here. And we want to know what it's going to form. All right. Well, remember, things that are negative charged like to act as a base, and they want to grab an H from somewhere. So I see this negative charge. It's going to grab any H that you want. Let's use this one because it's closer. And then don't forget what happens to these. This bond right here, once it grabs the H+, that's going to go down there onto the carbon. All right, so we'll get a C, double bond it to a C, to an H, to another H, to another H, and then again, this bond now becomes a lone pair. And we have a negative charge on the carbon. Plus, we now have an H bonded to another H, or you just write H2. So that was A here. Now, it says determine the direction of the equilibrium. Oh, what a great question. So let's go ahead and look at the acids that we have. We have 2 acids here. We know that this is the one that gave off an H, so this is one acid. And then we have an acid on the other side. Our acid, whichever direction this is going to go, depends on which one's the stronger acid. Is this hydrogen the stronger one, or is this hydrogen? Now I kind of want to redraw it so it's like H to an H, like that. Okay, so which one's stronger, that one or that one? We're going back to our table, but I'm sure you already memorized by now. We have the double bonded carbon to a hydrogen. This gives it a 44 pKa. And here we have an H to an H, which gives it a 35 pKa. Which acid's stronger, left or right? Hopefully you agree this one's stronger, which means this one's going to be the one giving off the acid the most, and the direction of the reaction will go that way. This one wins. In a battle between this way and a battle between that way wins, going to the left. All right, we do the same thing for B. Here we have a C, H, 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 and an H, plus OH minus. Very strong base. And we're asking ourselves what's going to happen. Remember, This negatively charged thing is going to grab a hydrogen. You could have chosen any of them, and then that bond is going to go onto the carbon. So for carbon, 3 hydrogens, a new bond, and now it's the negatively charged thing, and we have water. Okay, so our 2 acids are this one that gave off an H, and then this one that now took on an H, but now if it went back this way, it would have to give off an H. So these are our 2 acids. Let's look at the pKa's of these. The pKa of this one, the methane, is going to be 50. It's that alkane. The pKa of this is 15.7. It's water. All right, so your question is which one's going to win, left or right? Remember, the lower the number, the stronger the acid. This one's going to win, and the reaction will also go that way. All right, so it says, draw the products of each reaction and determine the, oh, we already did that, 4 factors of acidity that are 4 factors that affect the acidity of HA. In other words, how strong an acid is. Elemental, inductive, resonance, and hybridization. Elemental effects depend on what that H is bonded to. So for example, if it's bonded to something, I don't know why this really bugs me. Here we have a C to an H, an N to an H, an O to an H, and here they flipped it around. Let's do an F to an H to make it a little easier to compare. So here we're looking at the carbon, the nitrogen, the oxygen, and the fluorine. Remember that up and to the right of the periodic table, where we talked about cannot clean out fridge, F being the highest, this is the most electronegative element. So if you have a hydrogen bonded to something super electronegative, remember, electronegative things like electrons, right? So here we have an H, or an F to an H. We know that the electrons are moving this way towards the fluorine, right? Fluorine loves electrons because it's electronegative. That means it gets a really big partial negative charge. In fact, it sucks so many electrons away that it pulls them away from this hydrogen, and this hydrogen's like, bro, why don't I get any electrons? And then it's happy to be taken on by something else that's negatively charged because that actually wants it. This is a partial positive. All right, and that's why this is a really strong acid, and this one, which doesn't have as much of a pull between the two of them, is not as strong. So those are elemental effects, depending on which element something's bound to. Using that information, let's look at this. Which hydrogen is most acidic? Carbon is not nearly as electronegative as oxygen, so that hydrogen is going to be the most acidic because it's bound to an oxygen. Now here we have a hydrogen to an oxygen. We know these carbons aren't going to be the same, or aren't going to be considered comparatively. And we have a nitrogen. What's more electronegative, oxygen or nitrogen? Looking at that periodic table. Or the cannot clean out fridge. Hopefully you agree oxygen is more electronegative, and therefore this is going to want to be given away more readily. And that's why that's your answer there. Okay, how are we doing? All right, inductive effects. So kind of by a similar principle, but not directly the atom that it's attached to, is inductive effects. So for example, here you can see this ethanol, just regular ethanol, just kind of hanging out. Hydrogen, it's still relatively decent acid, right? It'll give away that hydrogen. But then if you look over here and you add a few fluorines to the end of it, boom, just like that, it became a stronger acid. Why? Kind of the same reasoning. The electron density is going this way. And if the electron density goes that way, this guy's like, dude, why are you leaving me? And so it goes and seeks other electrons in another atom. And so it'll easily leave. All right, so this one is a stronger acid again because it's got those on there. Using that information, let's go ahead and answer these. And A and A, these are all the same except this has chlorine and that has fluorine. Because fluorine's more electronegative, it's pulling the electrons more. And therefore, so this is a much bigger dipole than this one, which is like a smaller one. And that's why that is a stronger acid. So this is your answer. All right, the next one. So let me take a second to explain this. I in better terms. I haven't really thought through this one very well and how to explain it, but if you pull two ends of a magnet and they're like kind of close, right, you can feel that effect. But as you pull them further away, or farther away is the better grammatical term, as you pull them farther away, guess what does happen to that connection between them? Hopefully you realize as you pull them farther away, eventually there's no connection. You don't even feel that they were magnets at one point, right? And so the farther away those inductive effects get from the hydrogen you're looking at, in this case we're looking at that one, the farther away you get, the less of an effect the inductive effect has. Therefore, this one is a stronger one because those CLs are closer and they can have a really good effect on it. Over here, again, the farther away you get, the less impacted this hydrogen is by the polar, by the electronegative pole of the chlorine. Resonance effects. So another thing is resonance effects. I didn't have an example problem here, but it's because I want to show you each of these individually. So let me grab my paper again. All right. So in this case, we have two things we're looking at. This guy and this one. Okay, and I want to know which one's a stronger acid, even though I already told you. So remember, an acid, what makes an acid is it gives off H+, so this guy's going to go away. And eventually, once this guy goes away, its conjugate base would be this. And this one's conjugate base, once it loses an acid, so remember you have those lone pair, and I should have done that here. I know we're just getting used to it, so I want to be a little better. So this H goes away, you're left with those electrons there, and that's why you got this. And this one, we'll put those electrons there, I'll put those there. So again, we have this, but now the H goes away, and those electrons go there. So we have a negative here, but we also have this oxygen up here. If I asked you which of these two can resonate, I hope you agree it's this one. Remember, these electrons can go down there, those electrons can pop up there, and you can have a resonance structure. And if you have resonance structures, remember what I said about stability? This is going to be more stable. And because it's more stable once it gives off H+, it's more likely to give off H+. It's cool with giving off H+, because it's still going to be stable anyways. It doesn't bother it that much. And so because of that, this one is going to be a stronger acid. Well, really, I should point to that one. So hopefully that makes sense. Those are resonance effects. So if the resulting thing, once it gives off an H+, can resonate, then you know that that's going to be a more stable thing, more stable molecule. All right, and hybridization effects. This one's actually relatively quick to go through. So if you have a single bond, it's got a really weak acidity. A double bond, a little better, and a triple bond is far more acidic. And that just goes right along well with the S character that we talked about. Remember, singly bonded carbons, those are going to be sp3s. Double bonded will be sp2. Looking at this, excuse me, looking at this carbon, it's got 3 things around it, and this one only has 2. This is sp. All right, so sp, the more S character something has, this one has 50% S character, whereas this one only has 25%. This one will be a stronger acid. All right, and that's because it has electrons around it to stabilize it. All right, now we can rank these in terms of their most acidic hydrogen atoms, so kind of putting some of these together. All right, so I'm looking at them. They kind of all look really similar. Like I can look at OH and NH, and it reminds me of that one problem we did where we know that this one's going to be more acidic than that one because this is an O. And remember, if you have an H bonded to electronegative thing, the more electronegative it is, the stronger that acid will be. So this is a stronger acid right here, but then I look and see that these two are very similar, except this one has a chlorine. What did we say about chlorines or fluorines or putting electronegative things? It causes an inductive effect. So this not only has elemental, which they all do, because all these hydrogens are bound to something that's not like a carbon. Elemental and elemental. This one also has inductive, meaning that chlorine is pulling electrons away from that hydrogen, in addition to the oxygen pulling electrons away. So this is going to be your strongest. We already knew this one was stronger because it's an oxygen. So this is medium, and this is our weakest. Let's answer the question because it asks us to do it increasing acidity. So A is the strongest, followed by B, followed by C. That would be your answer. All right, moving on to Lewis acids and bases. Okay. So Lewis acids and bases, which you'll actually get to know, and I probably should have put this earlier, but a Lewis acid is actually called an electrophile. Phile meaning love, electron, love. All right, so a Lewis acid loves electrons, and a Lewis base, it despises them. No, it just gives them away. It's cool with giving them away. Okay. In order for something to love electrons, it's got to have an electron deficient site. Like it's got to have a positive charge, or maybe a really strong partial positive charge. In order for it to give electrons away, it has to have plenty of electrons to do that. So in other words, it's got to have, just like a regular base, just like the Bronsted-Lowry bases we just discussed, it's got to have a lone pair, a double bond, or a triple bond. Okay. Okay, so some common Lewis bases. Things with negative charges are going to be a really common Lewis base. And this is also called a nucleophile. I did a really bad job here. I'm sorry. I got ahead of myself. I have this written later. But electrophiles love electrons. This is where we're going to have like positively charged things. And nucleophiles are generally negatively charged things. Okay, so these are common Lewis bases. Again, they have to have the negative, the lone pair, or a double or triple bond. So you can see all those here. In this case, we have Bronsted-Lowry acids, which means there's a partial positive on them, and there's also, because it says they're actually both. Let me do a better job drawing this out. Okay, so water, you know that this is a partial positive, this is a partial positive, and this is a partial negative, right? So this can act as an acid with its partial positive site, or it can act as a base with its lone pair. And this one, same thing. You have CH3 to an O to an H. This is partial negative. This is partial positive. So you have a partial site, and you also have a lone pair. So that's why these can actually act as both. And here you have Lewis acids that are not Bronsted-Lowry acids. They're not also Bronsted-Lowry. So you have F, 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 and then notice that it doesn't have an H on it, so it can't act as a Bronsted-Lowry acid, but it does have an electron deficient site. Remember, things like to generally have an octet. This one doesn't have an octet, and even though it doesn't have a formal charge, anytime we have, and I'll draw this one to make some more sense of it, anytime we've got these trigonal planar things, guys, the BF3 or the ACl3 or the AF3 or the BCl3, those are going to be Lewis acids, but not Bronsted-Lowry acids. All right, so let's go ahead and see what happens when we put these in reactions, because I think it's better just to put them into practice. So here it says for each reaction, label the Lewis acid and the base, and use curved arrows to show the notation. So again, you're going to want to look for the acid, you're going to want to look for something that can accept electrons. So it's going to be either electron deficient, meaning it's got a positive or a partial positive charge. All right, or the Lewis base is usually going to have the negative charge, the dots, the lone pair right here, the double or triple bond. All right, so right away I look and see the only thing with like lone pair is this guy, and I know this one's got to be the base. I know therefore this one has to be the acid, and that's good because I already memorized it as one of those suckers up there. All right, again, you can only move electrons from, or arrows from the electron side to the other side. So I'm going to move this from there to there. And that would give us this. I shouldn't have given you this. I wish I would have covered that up. But anyways, lesson learned. You can see that this lone pair right there forms a bond with that boron. And now the boron has a negative charge and the oxygen's left with a positive charge. A kind of similar thing happens here, where we've got this, what we'll eventually come to know as carbocation. It's a positively charged carbon ion. And this negative right here is telling us that this sucker's the base. And again, we have an electron deficient site telling us that's the acid. And that goes in there, grabs onto there, boom, shakalaka, we got that. All right. So, yeah, let's move on to this one and see if this helps. Again, this is where I was really going to go over it, but Lewis acids are called electrophiles. They like electrons. Bases are called nucleophiles. They're cool with losing electrons. All right, so now we get to actually guess what's going to happen here. So I see right away we got a lone pair there. This one we don't. Again, this is one of those trigonal planar things. BR, BR, BR. I know you can't read it very well, but it's a boron with 3 bromines on it. Okay, so the only one that can move electrons is this one right here, right? So this has to be, and it asks us now to do a nucleophile and electrophile. I kind of like looking at the electrophile first. It makes the most sense to me. This is the one that's going to take on those electrons. This is the one with the positive charge. This is the nuke. Or excuse me, oh my God. This is the electrophile. It's going to take on the electrons. It's got a positive charge, and it's like, please, please, come over here. It loves electrons, and these electrons are like, cool, dude, we'll go over there, and they go over there. And this is the nucleophile. Maybe you think of it like a nuke going and hitting a positive site. Boom, and hitting over there. And now we have O. In fact, I'm going to redraw it over here where I have a little more space. All right, so when it goes over here, we have dung, dung, O, dung, dung. We still have that lone pair there, but now we've attached it to the boron. And don't forget the boron has 3 bromines on it. It's also changed the charges. So the nucleophile here, when it hit there, it gave this one some extra electrons. Now it's got a negative charge, and the formal charge of this oxygen is now positive. And you could have calculated that as well, valence minus sticks minus dots. All right, let's do the same thing over here. You get so good at drawing hexagons in this class. I'll draw it the way they drew it, like this. And now you have an AlCl3. Sorry, it's hard to write really small with the marker, so I wanted to do a better job here. Okay, so you have AlCl, or Al with 3 Cl's around it. I don't know what that is, but it's there. And you're reacting it with this. This is the only thing that can do anything. This is the electrophile, because it's got a partial positive charge. That's going to go in there and hit that spot. And now we're going to have, again, sorry, I don't know how that happened. We're going to go over here. And this is going to be where it gets really fun. Sometimes I like to draw the original thing. And we knew it was double bound to an oxygen right there. I already had that lone pair. That didn't do anything. But this lone pair grabbed onto aluminum. and that aluminum had 3 Cl. So practice doing this one if you haven't, because this is only going to get way crazier throughout organic chemistry. This now became a negative site, and that had a positive site. So again, if you calculate valence minus 6 minus dots, you'll get a negative, and there you'll get a positive. All right, is that about it? That's about it. So mainly I want you to be able to recognize what's a nucleophile, what's an electrophile. Electrophiles tend to be the positively charged things or have partial positive charges on them. And nucleophile has that extra set of lone pairs or double, triple bonds that they can use. Okay, so this is the most important part right there. All right, y'all, have a great day. I'll talk to you later.